Hey everybody, it's Wednesday, March 3rd, and as you can see here in the aim today, our goal for today's video is to start talking about rotational motion. Now, as is suggested by the aim, the key to understanding rotational motion is by using our understanding of linear motion. But before we get into rotational motion, I'd like to just make sure that everybody understands the basic concept of what was said yesterday about center of mass. If you remember, what I was trying to get across about why center of mass was taught yesterday is that most of the AP physics test center of mass questions have to do with momentum. And so, as we said yesterday, center of mass is very closely related to the concept of momentum because what you need to know is that if there are no external forces acting on a system, the momentum of the center of mass is conserved. Additionally, then, we can say if the mass of the system does not change, in order to keep the momentum of the system the same, the velocity of the center of mass must remain the same. And that actually comes up in a large number of questions that you could expect to see on the AP test. Now, whether you realize it or not, that comes up in questions that very obviously seem like they're just asking you about the speed of the center of mass. And they also come up in these weird questions that we talked about yesterday with the man walking on the dock. The man on the dock problem is definitely a problem you are going to see on the momentum test. There is going to be one multiple choice, and you will not see another example of this before the test because there is only one version of that multiple choice question that exists. And we're going to save it for the test just to see how much everybody understood this discussion here. But what I can tell you is the whole point of the problem is that the man and the dock are initially at rest, standing together. And then once there's a force exerted by the man's feet on the dock, they start to move in opposite directions. It's sort of like an explosion problem. And so the thing that you need to realize is that because the momentum of the center of mass was originally zero, then that means the momentum of the center of mass at the end is zero. And the key point is if the velocity of the center of mass is originally zero, then the velocity of the center of mass will always be zero, which means it's going to stay at the same location. What's particularly nice about the multiple choice question that the AP test is going to ask you is it stacks the answer choice one on top of the other. And so I think it'll be pretty easy looking at the four diagrams to be able to say, well, if the center of mass has got to stay in the same spot, it's got to be here, and then just going down the line and seeing where the center of mass is in the same spot. Again, you'll see it on the test. If you get it, you get it. If you don't, hopefully seeing it in the form of a question on the test will sort of help you realize how not that terrible it actually is, and then maybe that'll help you for the test. This point is important, and I forgot to put this up at the very end of the video yesterday, so take a second to pause this video here and write that down, and when you hit play, we'll move on. Okay, so just to wrap up this concept of center of mass here and officially put it to bed, I want to take a quick look at two more problems before we talk about rotation. These are going to be two quick ones, though, so I'm going to show them to you, give you a minute to answer them, and then we'll move on. The first one is here. Question says, Elon Musk's Falcon Heavy rocket with a mass of m is moving with a speed v. When the final stage separates from the payload, the two pieces are exactly evenly split into two sections, both with a mass of m by 2. So basically, they split with half the mass. If the original mass was 1,000, it's two 500-kilogram pieces. Anyway, it says if the rocket moves backward with a speed of v, then what is the speed of the center of mass? Take a second to pause this video here and write this question down and try your best to come up with an answer. When you hit play, we'll go over it. The key to answering this question correctly is recognizing the importance of this piece of information right here. The problem says the whole rocket, the two separate pieces, when they're together, move with the speed of v. That means this is the original center of mass speed. And even though there is a quote-unquote explosion that's happening here between the two pieces, which is ultimately why they separate, there are no external forces exerted on the rocket. The whole point here is this explosive force that separates the payload from the final stage of the rocket is an internal force. And that means the momentum of the center of mass is conserved. And if the center of mass was originally moving with a speed v, in order to conserve momentum, the final speed has to be v because the mass of the system did not change. That's the point. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, one last question here. Same prompt, Elon Musk's Falcon Heavy rocket with mass m is moving with the speed v. When the final stage of the rocket separates from the payload, the two pieces are exactly evenly split into two sections, both with a mass of m by 2. If the rocket moves backward with the speed of v, then the speed of the payload is... I want you to take a couple minutes to pause this video here and think about how you would answer this question. When you think you've come up with a strategy, execute the strategy. And when you think you have an answer, hit play, and we'll go over it. So the basic thing you need to realize about this question is, although it does seem like a straight up center of mass question, which it is really to some degree, you have to recognize here that this, at the end of the day, is a conservation of momentum problem. Basically, it's like an explosion problem. Now, notice the explosion problem always has the object starting off at rest, or at least most of the time. So really, if you want to say this is like a perfectly inelastic collision in reverse, well, that works too. At the end of the day, it's important to realize the reason why we were talking about center of mass in this unit is because the momentum of the center of mass is conserved in the absence of external forces. And that means the initial momentum for the system is equal to the final momentum for the system. The system initially is a rocket of mass m moving at a speed of v. At the end, we have two objects. Both of those objects have a mass of m by 2, and we are going to multiply them by whatever velocity they end up having. So the first half of the rocket, with a mass of m over 2, moves backwards with a speed of v. And the other half of the rocket, the payload specifically, with a mass of m over 2, moves forward with the speed, which we're just going to label as v prime. Now, notice I said here the payload moves forward, and that may not be obvious to you, but it has to. If the whole thing, there's the separating line, is moving in this direction with the speed of v, and then eventually the two pieces are moving separately, and one of the parts is moving backwards with the speed of, or with a velocity of negative v, that means this piece has to be moving forward, and it has to be moving with a velocity that's faster than v in order for momentum to be conserved. Now here's the deal. If you take a look at this problem, all this really is math. Here, I have mv equals negative 1/2 mv plus 1/2 mv prime, which is the thing that I'm looking for. And if you add this term over to the other side here, then you get 1 mv plus half mv equals 3/2 mv equals 1/2 mv prime, which is what we're looking for. We're just adding that term over to the other side. And now notice here, those masses cancel. And so the only thing we have to do here to solve this for v prime is multiply both sides of the equation by 2. And so we end up getting v prime equals 3/2 times 2. And notice when we multiply this side by 2, the 2 in the denominator is going to go away, meaning v prime is 3v. Basically, and that should make sense, that in order for the whole system to maintain the same amount of momentum going forward, with half of the piece going backwards, the other half of the piece that's going forward has to have a much larger velocity in order to produce the same amount of momentum. Despite the fact that that may seem like a new question, it's really not. And that's an important thing to recognize. Take a second to pause this video here and write down any part of this that you may want to, a summary or a little note for yourself or whatever. And when you hit play, we'll start to talk about rotation. At long last, the day has finally come. We are ready to talk about rotational motion. Isn't that exciting? And so, really, here, I just want to jump right into it. This is the second to last unit. We are really getting down to it. Now, there's a lot of new stuff in the rotational motion unit, but I really want everybody to realize you know most of this stuff already. It's going to look different, but you know it. Remember that. First question, what is rotation? If an object is rotating, what is it doing? There's a lot of different words that you can use for this, but let's just go ahead and say rotation can be described as a turning of an object about the same axis. So if an object is rotating, it's going to be turning about a particular axis, and that's going to be a sort of repeated motion. A pretty obvious question now we can ask, what do you think will be the most important topic that we've covered so far that will have relevance for rotation? And it's important to realize here, if we are talking about like a disk, and we're saying that disk is rotating, any point on the rotating disk is moving in a circular path. And since points along the rotating body will experience uniform circular motion is going to have a heck of a lot of relevance to this unit. And that's what I mean by a lot of this stuff you already know. Take a second to pause this video here and write that down. And when you hit play, we'll move on. This is probably the most important note we are going to write for this unit. This is something you absolutely need to internalize. Every rotational quantity of motion has a complementary quantity from linear motion. Every single thing we're going to talk about basically has a rotational version. It's the rotational version of some linear quantity. And so it's important to realize, like, for example, we just finished up the unit on momentum. In about a week, we're going to talk about something called angular momentum. A lot of the stuff you know about linear momentum can be said about angular momentum. Basically, everything that we're going to talk about now is just going to be the rotational version of linear quantities and concepts. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so to that effect, we have another big note here, which says, in exactly the same way that we have the concepts of position and displacement in linear motion, in rotational motion, we have the concepts of angular position and angular displacement. Very important point. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so despite the fact that I said a lot of this stuff you already know, which is true to some degree, this is still a new unit. And so a lot of what we're going to be doing today is just defining the basics so we can eventually get to the good stuff. One of the things that we're definitely going to want to define right off the jump is angular position and angular displacement. The first thing we'll say here is that angular position represents the location of some reference point on the rotating object relative to some polar coordinate axis. Basically, when we have a rotating object, we're always going to have to pick some reference point on the object. Like, really try to imagine a disk that was rotating. As is always the case when you're trying to make measurements, you need a coordinate system and you need a reference point. And so we're just going to say, like, oh, we're going to pick this point. And so that point has what we refer to as an angular position. Essentially what we do is we set up a grid and we label various angles along that grid. Obviously that is an awful picture. I'm going to show you a better looking picture here in a second, but that's the idea. Angular displacement then, in like a very logical way, if you know what the word displacement means in the linear context, angular displacement represents the angle through which that reference point has rotated. That's it. Position is where an object is. In a linear coordinate system, displacement is the change in position. Angular position represents the location on like an angular or polar coordinate axis. And angular displacement is the change in angular position. That's all. It's the angle through which the thing has rotated. And so to be clear about what I mean by some polar coordinate axis, basically what we have is like a pretty similar XY system here, but instead of labeling the X and Y axes in meters like we usually do, now we're labeling them with angles, with 0 degrees here, 90 degrees here, 180 degrees here, 270 degrees here, and then when we get back over here, we have 360 degrees. So this object, this red line right here, let's say this is an object, like a disk, and it's rotating. And let's say it's rotating this way, clockwise. Let's say this is our reference point. We would say the angular position here, you can just tell by looking out this way, would be 60 degrees. If eventually the thing has rotated to here, well, then its angular position would be 330 degrees. Or you could say negative 30 degrees, but that's not an extremely important distinction. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, I want to be clear about one thing before we move on, because what I just showed you is a little misleading. This is an example of your first polar coordinate axis. It is also the last polar coordinate axis that you will see labeled in units of degrees. In this course, the angle for rotational motion is always measured in radians. Radians is the more natural unit in physics. When we're talking about a thing rotating, we're talking about its angular position, that is going to be measured in units of radians. And so the polar coordinate axis is going to look like this, where over here, where we had 0 degrees, we have 0 radians. Over here, where we had 90 degrees, we have pi by 2 radians. Over here, where we had 180 degrees, we have pi radians. Over here, 3 pi by 2 radians, and then 2 pi over here in the place of 360 degrees. That's the idea. It's also important to realize, and this is the last thing we'll say over here, when we're talking about angular displacement, which I'm going to show you an equation for in a second that should look familiar, you also have to remember relationships from math. If we really want to see how the angular displacement, which we can label theta here, compares to the arc length, you have to remember that relationship from math. Ultimately, this equation between the arc length, the radius of the circular arc here, and the angle looks like the equation for the circumference of a circle. The circumference of a circle is equal to 2 pi r. And so what that means is the part of the circumference, or the section of the circumference, or the arc length is equal to the angle, which we're going to label theta here, times the radius, r. And so we'll just write that equation down, we'll label it, we will revisit this later on. S here is going to be the arc length. That is going to be measured in meters. Theta is the angle, or I should really say the angle / angular displacement. And that's going to be measured in radians, abbreviated rad. And r is going to be the radius, measured in meters. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so that brings us to our basic definition of angular displacement. You can write this under the heading angular displacement. Angular displacement represents the angle through which a reference point has rotated. I'm going to write in parentheses just to familiarize it and bring it back to things we've already said about displacement. It's the change in angular position. And so in a totally unsurprising fashion here, the symbol for the change in angular position is going to be delta theta. It's actually 2 Greek letters. The equation, in a rather unsurprising turn of events, is going to be delta theta equals theta final minus theta initial, where theta final, or theta with the subscript f, equals the final angular position measured in radians. Theta naught is the initial angular position measured in radians. And delta theta is the angular displacement, also measured in radians. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Let's take a look at a problem. This problem here says If a point on a compact disk is at the initial angular position of 4 radians and a final angular position of 7 radians, what is the angular displacement of the compact disk? Now, let's just quickly zip through this because there's not even really any reason why I should be showing this to you, but just so you at least see what the thing looks like. Theta naught here is going to be 4 radians. They tell us that in the problem. The final angular position, as they also tell us here in this problem, is 7 radians. And we're looking for the angular displacement here, which is delta theta. So the definition of angular displacement, delta theta, is the final angular position minus the initial angular position. And so that means here we have a delta theta of 7 radians minus 4 radians equals, you guessed it, 3 radians. Really, honestly, this is about as easy as it gets. There's not a whole lot to say about angular displacement. Let's just take a second to ask a quick question to make sure we all get it before we move on. And that question here, burning question, if you remember CD's burning question, you probably still wouldn't find it funny, but anyway, has the CD completed 1 full rotation? Yes or no? Take a second to pause this video here and think about it. When you think you got an answer, hit play and we'll go over it. The answer here is no. The disk has not completed 1 full rotation. 1 full rotation in radians is 2 pi radians, or about 6.28 radians. Since this disk experiences an angular rotation of only 3 radians, it doesn't even experience half a rotation. The angular displacement, really here I wrote rotation, but if I'm being totally precise, that should probably say displacement. The angular displacement is only 3 radians because 180 degrees is pi radians, and that's 3.14 radians. This is only 3, so it's less than 180 degrees. Of course, you could use the relationship between radians and degrees to convert it if you want, because as we mentioned here in the very beginning, 1 radian is 57.3 degrees, but for the purposes of this question, not even remotely important. And that's really all that needs to be said about angular displacement. That brings us to angular velocity, and this is what we will finish up today's video with, because this stuff, as you might imagine, is pretty simple and straightforward as well. Angular velocity is a measurement of the rate at which an object experiences a change in its angular displacement. Of course it is. Linear velocity is displacement over time, and so it shouldn't come as a surprise what the equation for angular velocity is. The first thing we want to say about angular velocity is this is the symbol. This is a lowercase omega. This is a Greek letter. You will notice here a lot of the symbols for rotational quantities are Greek letters. It's fine. It's an omega. It kind of looks like a W. It's a little fancy like. You will see it in the reference table if you really want to know how it's printed. This is what it looks like in PowerPoint font. The equation, rather unsurprisingly, is delta theta over t. If regular velocity is the change in position over time, then angular velocity is the change in angular position over time, or angular displacement over time. All of those things hold. Position is where it is. Displacement is change in position. Velocity is the change in position over time or displacement over time. And so angular position is where it is angularly, if you will. Angular displacement is the change in angular position. And so angular velocity then is the change in angular position over time or angular displacement over time. And so in this equation, we've got a lot of terms here now with the 2 different versions. Delta theta, of course, is angular displacement measured in radians. Theta final is the final angular position. Theta initial is the initial angular position. T is the time interval measured in seconds. And so angular velocity is going to be something measured in radians divided by something measured in seconds. And so the unit here is going to be radians per second. And so that's what I've written here at the bottom. The unit is radians per second. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, something else we should be clear about while we are on the subject here is that velocity is a vector. So angular velocity is a vector. Now, I want you to think about what the sign of a vector usually shows you. It shows you direction, right? So if we're talking about the angular velocity of something that is rotating, then really we're going to be talking about the direction of the rotation, whether the thing is rotating clockwise or counterclockwise. One of those is positive and one of those is negative. Which one do you think is going to be the positive one? To my mind, it makes sense that clockwise would probably be positive, but it's not. It's counterclockwise. So if something has a positive angular velocity, then its angular displacement is counterclockwise. And if it has a negative angular velocity, it's because its angular displacement is clockwise. And I'll write in here counterclockwise and clockwise. Take a second to pause this video here and write that down. And when you hit play, take a look at a problem. Okay, now you'll notice this about some of the rotational motion problems we're going to solve. There is a rotational motion packet. It's actually really long. There's a ton of pages. But some of the rotational motion questions that we are going to do on homeworks and actually as we go through this material is going to be in the gravity and uniform circular motion packet, especially when we're still just talking about like regular motion. And so this is one of those examples. This question is in the gravity and uniform circular motion packet. It's on page 10, number 1. It says, A, find the angular speed of the Earth's rotation about its axis. B, how does this rotation affect the shape of the Earth? We're going to start just by looking at A. Now, what I like about this question is it says, find the angular speed of the Earth's rotation about its axis, and it gives you nothing. You are expected to know some things about the Earth. The Earth rotates, yeah? And so you're expected to know some facts about the Earth's rotation. And the most basic fact is that the Earth rotates once a day. That's it. That's all you need to know to be able to answer this question. So if the Earth is rotating one time in a day, that means the angular displacement is going to be, well, one complete rotation, 360 degrees, or 2 pi radians. And for the time, well, that's a day. But of course, if we're going to find the angular velocity, which is omega, we have to do that in radians per second. And so the first thing that we need to do for this question is to convert a day to seconds. Now, when we are going through the dimensional analysis part in the very beginning of the year, everybody in this class usually makes fun of me because I have memorized the number of seconds in a day. And people say that's useless information. You've wasted your time by memorizing that. Not so. One day has 86,400 seconds. Since I'm assuming most of you don't know that, you could always use the idea here that a day is 24 hours, and then, of course, 1 hour is 3,600 seconds, right? 60 minutes in an hour, 60 seconds in a minute, so you get 3,600. And, of course, 24 times 3,600 is 86,400. And since the day here cancels the day there, and the hour there cancels the hour there, we're left over with units of seconds. So 1 day is 86,400 seconds. Simple enough. And so the angular velocity here is going to be delta theta over t. And so that means the angular velocity is going to be 2 pi radians over 86,400 seconds. And it should be noted that, yeah, this number is going to be small. The Earth is not rotating very fast. It only completes one rotation in a whole day. I want you to actually stand up and spin yourself around one time. Imagine if it just took you one whole day to spin that same distance, one rotation. You'd be spinning remarkably slow. The answer here, when you do that math, is 7.27 times 10 to the negative 5 radians per second, which, if you're interested, is about 0.004 degrees per second. So really, really small. And that's really it for the angular velocity calculation. Now, before we go, we've got one more question to answer, and that would be part B. How does this affect the Earth's shape? The answer may be surprising, but it's that the shape of the Earth is changed as a result of its rotation. It is not a perfect sphere. The Earth is a sphere that bulges around its center and thus has the name an oblate spheroid. The Earth is an oblate spheroid because it is rotating, and so it bulges at its equator. Let's take a look at a simple demonstration of this. Notice here, this person is showing you this disk here, which she's about to spin, and she's saying basically that if you consider it from the reference frame of the little disk here, then it's in an accelerated reference frame. So there is a centrifugal force acting on the object, and look at that, it bulges at the equator. Another way to put it is just that the objects have inertia, and the inertia causes it to go in a straight line, and so you have like tugging at the outer edges, which is why it bulges at the center. And that's it, equatorial bulging. Now, I suggest you be careful when you're Googling this, because I used this feature, being able to search things on a Windows computer like this, and I typed in equatorial bulging here and found this result from Bing. And this is a flat Earth video about how the Earth is definitely not rotating because the equatorial bulge would be 14 miles. And that means like, I can't even believe I watched the whole thing. They are saying that like, well, the mountains would be 14 miles higher. And like, how would that be possible? I think the point is that the Earth has plates sitting on top of like magma, which is liquid. And so it's not just like a solid hunk of something. But what this person ends up going to show is irrefutable proof of how the Earth is not rotating, is that they take this ball and the ball is like soaking wet, but it's porous. And so then they take it and they say like, oh, look, all the water flies off of it. If the Earth was rotating, wouldn't that mean all the oceans would fly off of it like this thing does? And of course, then the answer is no, because of, gravity. The gravitational attraction between the water and that little ball is not anywhere close to the gravitational attraction between all of the water on the Earth and, the Earth. So, dear God, the Earth is round and it rotates. It's 2021. And on that happy note, that's it for today. We will pick back up tomorrow, basically by transitioning this discussion into the realm of accelerated motion. Have a good one, everybody.